Well, good morning. My name is Duan Brown with NASA's Office of Communications at NASA headquarters in Washington, D.C. It is my honor and pleasure to be your Master of Ceremonies for today's event here at the Newseum in the nation's capital. It's all about comets today. I want to welcome our studio audience here. I also want to welcome our national audience viewing this program via NASA television and our worldwide audience viewing this via the agency's website at www.nasa.gov. We have a lot to cover today about comets. And before we officially declare a class in session, it is my pleasure to give brief remarks and acknowledgments, Joe Urschel, Senior Vice President, Sales and Marketing for the Newseum. Joe?
Well, let me add my welcome to everyone to the night studios here at the Newseum. If a institution that's only been open 2.5 years can have a long history with anyone, we have indeed had a long history with NASA. We've hosted many of your great events here and worked with your great staff on any number of programs and stories. You no doubt are familiar with the expression, it's not rocket science. And I confess to having used that expression several times myself over the course of building this museum. But your work really is rocket science, and we appreciate it so much, and we are just awestruck by the things you've been able to accomplish over your long history. And it is our great pleasure to help you celebrate them here at the Newseum. The Newseum is not rocket science, but our mission, I think, is similarly difficult, if maybe not quite as complicated. What we try to do is promote the idea of a free press being the cornerstone of democracy, both here and worldwide. And as you may have read, you know, the media is not the most popular institution in the United States nor in the world, but we think the work that is done by members of a free press and oftentimes members of a repressed press is important to the development of the world, both scientifically and socially. And what we try to do with our museum here is tell the history of the world through recent news events and explain how the role of the media played an important factor in bringing that news to people. If people don't know what's gone on, it's still news to them. And if people don't know what's happening with their society, be it scientific or political, there's no way they can get involved in it. And we really congratulate NASA for providing us with so many great news events of great human accomplishment that we can use here at the Newseum and celebrate in its role for the development of worldwide knowledge. So with that, I'd like to thank you for the work you've done and the work you continue to do. And I'm sure there'll be some news from this event today that hopefully will end up someday on display at the Newseum along with all of our other great stories. So thank you all for coming. I hope your event goes well, and we appreciate everything you've done. Thank you.
And thank you, Joe. And of course, we're always honored to be here in this incredible organization and facility. Okay, so we're going to get started, ladies and gentlemen. Today you're going to get firsthand insights about comet discoveries, observations, and encounters over the past 25 years and hear from the foremost experts for the next two comet encounters occurring on November 4th and another in February 14th of next year. I'm going to give some brief backgrounds for today's presenters, and if you want to get all of the details on these incredible individuals, you can go to www.solarsystem.nasa.gov for their complete bios. You can also read about the incredible activities that are coming up at NASA for the year of the solar system. So let's get started. It's all about comets. First up will be Dr. James L. Green, Director of NASA's Planetary Science Division at NASA headquarters. Dr. Green, goes without saying, is an extremely accomplished scientist, and personally, he is one of the coolest guys I've ever met. He received his degrees from the University of Iowa and was personally mentored by the late Dr. James Van Allen. Ladies and gentlemen, please give a warm applause to Dr. Jim Green.
Well, it's a very exciting event. We're here today to celebrate the 25th anniversary of our first comet encounter. And to do that, we're going to look not only backwards, but forwards. We're going to take a little tour of some ancient history, try to put the context of what we now know about comets and how that's changed over time, and in particular, look forward to two upcoming encounters, as Duan mentioned, that will occur in the next 6 months. So, as Duan says, let's get started. About 5 billion years ago, as our solar nebula collapsed, creating the sun, the planets, their satellites, and asteroids, but it also created comets. And these comets coalesced in the cooler regions of that nebula, in the outer regions where icy gases along with rocks and dust coalesce to form a comet. With the occasional tugs from the sun of gravity to the point where they come inward, they begin to show, as they get close to the sun, and sublimate their beautiful long tails. Now, from early history, as humans walked the earth, they incorporated the sky into their culture and in their belief system. Well, unfortunately, comets got the bad rap. Nearly every culture in our history thought of comets as harbingers of gloom and doom. And let me just give you a couple examples of that. Here are some ancient images in Chinese text from well over 300 BC, displaying comets, displaying their tails. And the text tells us of the disasters that occurred that year, and probably in hopes of determining if a certain comet tail structure tells us a little bit about the disaster that may occur. If you were to be famous and really a well-known individual, you were associated with your death with the coming of a comet. Here is Caesar, Julius Caesar, who died in 44 BC. A coin commemorates his death with a beautiful comet, the comet's tail radiating in all directions as it passes in and around the sun. Montezuma believed that the coming of a comet was one of the major signs, one of 8 actually, that he should have recognized that as the Spanish came and nearly destroyed the Aztecs, once again, comets bringing on that harbinger. In addition to that, early painters even associated comets with disasters of climate, whether they're huge storms, whether they're floods, hurricanes, etc., but just complete chaos that was occurring, and it was because of the comet that was coming. Well, fortunately, some of these things started to get straightened out when Edmund Halley began to look at comets, trying to employ some of the Isaac Newton's now fundamental equations to their motion. And he began to notice that there were at least one comet in his list that he collected that seemed to reappear periodically, about every 76 years or so. And in fact, Edmund predicted when that next apparition of that comet would come by. And this was assuming that it had an elliptical orbit. He did a lot of calculations, and he even included the effect of gravity from Jupiter. Well, it turns out Halley didn't see that comet. He died well before that appeared. The comet did come within a day or so, as he predicted, and it's currently called Halley's Comet. What happened also to Halley is even in the newspapers. In fact, I'd be remiss if I didn't show some news articles here in the beautiful Newseum facility. But in the 1910 apparition of Halley, we see these fabulous articles. The Earth was to actually cut through the tail of the comet. So poisonous gases, of course, would be impinging on our atmosphere. Scientists had to come out in these articles and explain that wasn't true. Even an earthquake, which killed many in Costa Rica, scientists had to say, no, that comet that's coming had nothing to do with that. And so indeed, it was still in our culture, even as recently as the last 100 or so years. But comets today, the ones that are really beautiful, we observe these long tails only a few per decade. And in fact, now our modern set of observations are really changing this perspective. And what we're finding out, if we show the movie, even from our solar observing spacecraft, such as SOHO and STEREO, and in fact, this particular image, which will cycle, shows a comet coming in, but not coming out as it crosses in and around the sun. The sun's tremendous heat and light actually sublimates the comet away and destroys it completely. Now, over the last 10 years alone, by staring at the sun and seeing these comets come in, well over 1,000 comets have gone through this process and have disappeared. This changes our view completely of how ubiquitous these systems are. And now, with new spacecraft, starting from the International Cometary Explorer, ICE, 25 years ago, which will be discussed by Bob Farquhar, we're going to hear now much more about that science. What do we really know about comets and how important they really are in the origin and evolution of our solar system and perhaps even life here on Earth? And so with that, let me turn it back over to Duan to introduce our next speaker.
Thank you, Jim. Next, we have Dr. Anita Cochran. Is Assistant Director of the McDonald Observatory at the University of Texas in Austin. She received her PhD from the University of Texas and her undergraduate degree in physics from Cornell. And I have to tell you, while we were rehearsing, I told her she has this incredible smile that just makes you want to feel good. So you'll see that. Ladies and gentlemen, please welcome Dr. Anita Cochran.
Good morning. Well, comets are probably some of the most beautiful things in the universe. I'll go past the solar system into the universe. And they've been, because they show up suddenly and are so prominent, we have records of them going back many thousands of years, as Jim talked about. And this is an example of one of the best comets in the last several decades, and that's Comet Hale-Bopp. The domes are McDonald Observatory. I have to put in a plug for my own institution. And we get about one per decade that looks really spectacular like this. This is Comet West from 1978. This is not my observatory. This is the Very Large Telescope down in Paranal, Chile. This is Comet McNaught. And we see all these different behaviors. Of course, most of the comets that we fly missions to, unfortunately, are not these magnificent big comets, but we still learn incredible things about comets by looking at these. They're not only very beautiful, but there's a reason why we want to study them. And that is because, as Jim talked about, they were formed 4.5 billion years ago at the start of the solar system, but they weren't built as part just at the same time as planets. Instead, they're the building blocks of the planets of the outer solar system. So planets like Jupiter, Saturn, Uranus, and Neptune, they were started to be built out of comets or planetesimals, small icy bodies that are now, the ones that we see today, are the leftovers from the formation of the solar system. So the reason why we care to study comets is because they tell us about the conditions in the early solar nebula. And unlike the planets, which have undergone lots of change as the solar system has evolved, the comets have not undergone a lot of change. They're small, they spend most of their time out in the outer regions of the solar system, so they stay icy. And therefore, the comets that we see today coming into the inner solar system are very little changed from when they formed. And by studying them, we learn all about the origins of our solar system. So though most of us will tell you we look at debris, leftovers, it's very fundamental leftovers to understand where did we come from. And that answers one of the big questions that NASA's always been interested in, where did we come from? So that's why we want to study comets today. And the modern era, Jim talked about the history, but the modern era of comets really started in 1950. And it started with several important people. The person who's shown on this picture is Fred Whipple, and Fred Whipple is basically the person who came up with our concept of what is a comet. And as he's demonstrating with this picture, it's an icy snowball or a dirty snowball. That's probably a little small for a comet today. We wouldn't see that one, although I don't know where Fred got that large chunk of ice. But he claims he was riding his bicycle home one day at Harvard, and he was thinking about comets and realized that they have to be made up of a combination of ice and dirt. And that ice, as the comet approaches the inner solar system, gets heated and it's sublime. So if you took ice and put it on a table here, you turn it into liquid. But in space, because you don't have the gravity and you don't have the pressures, you go straight into, and it's very cold, of course, you go straight into the gas phase. So you go from the ice phase straight into the gas phase. And that gas will then take with it, as it flows away from the comet, which doesn't have a lot of gravity, it will take with it the dust and dirt that exists in the comet and form the tails that we see. And also the atmosphere that's an unbound atmosphere around the comet called the coma. So Fred was really the father of our current concept that comets were dirty snowballs. Going back again to a picture of comet Hale-Bopp, you see that in this spectacular example, you have the coma, which is the atmosphere around the nucleus is never seen from the ground. It's way too small. Nuclei of comets are sort of a few kilometers across, so the size of a small city. A big comet like Hale-Bopp is probably 30 kilometers across, so the size of a city like Washington, D.C. But as that material sublimes and takes with it the dust, you can form, but you don't always form, two different tails. The dust tail, the white tail on that picture, is dust flowing behind the comet in its orbit. And the ion tail is gas that's been ionized by the solar wind and entrained in the solar wind. It's been ionized coming off and follows directly outward from the sun. So that's what a spectacular comet looks like. But where did they come from, and what is the structure of the outer solar system now? Well, in 1950, it was also figured out where some of the comets came from. And that was done by a remarkable gentleman called Jan Oort, who worked on all branches of astronomy, but was very important for understanding the cometary orbits and where they came from. Now, comets, like the planets, all orbit the sun. And some of them are in the same plane as the planets going around the sun. That's called the plane of the ecliptic. But some of them come from random directions. Comet Halley actually goes in the reverse direction around the sun than the Earth does. Comet Hale-Bopp was 90 degrees from the orbit of the Earth around the sun. And with all these seemingly random directions, it was a difficult thing to understand where they come from. Well, Jan Oort, looking at the orbits of 19 comets, and only 19 comets, figured out that there's probably a reservoir of comets out way past the sun. Now, he didn't get exactly the right distance, but that's the limitations of the calculations of the time. We now know that what we call the Oort cloud, named in honor of Jan Oort, is a reservoir of comets, a spherical halo of comets at about 100,000 times further from the sun than the Earth. He also didn't realize at the time that the comets probably didn't actually form out that far. We now know that they actually formed in the region of the giant planets, and because of the pulls and pushes of gravity, they were thrown out to the Oort cloud. About 90% of them were lost from the solar system, and about 10% still live out there. That still leaves a lot of comets. That's of order billions and billions, as Carl Sagan would have said. So he figured out that there was this spherical halo of comets, and that explains their orbits. About the same time, Gerard Kuiper, who actually wasn't a director of McDonald Observatory at one point, didn't figure out what we now call the Kuiper Belt, but he said, you know, it makes no sense to have all these big planets and then nothing past the orbit of Neptune. Well, Pluto, but Pluto's tiny. There's got to be more material there. He wasn't able to follow up on that, but in the late 80s, people had been worrying about not only what must be out there, but also that there was a group of comets that didn't come from random directions, but instead were in the plane of the ecliptic, the same plane as the planets. And so they realized that there must be another reservoir starting from Neptune going outward that was in the plane. It was a disk of material, and that those were the things that fed what we call the Jupiter family comets, the ones that are in the plane of the ecliptic. And Duncan, Quinn, and Tremaine, who wrote the seminal paper in 1988 explaining all of that, gave the name to this as the Kuiper Belt, because it was named after Gerard Kuiper, who had posited that there must be material out there. Well, what is a comet? I've said it's a dirty snowball, but what does that really mean? It means that about 50% of the material in the cometary nuclei is probably ice, and about 50% is dirt. What do we mean by dirt? Well, same thing as we mean by dirt on the Earth. Silicates and olivines and all these kinds of things, some of them crystalline, some of them amorphous, no crystalline structure. But it's the ice that sublimes and carries away this material and is of interest to us. Well, when astronomers talk about ice, they don't necessarily mean water ice. Some of the ice is water ice, and probably about 80% of the ice is water ice. And about 20% of the ice is other things, carbon monoxide, carbon dioxide, formaldehyde, all sorts of things. And it was not the water, of course, that the tail of Comet Halley was going to bring to the Earth, but it was the hydrogen cyanide that they were really worried about. So these are the building blocks of the outer solar system. And one of the things that we started realizing as we studied comets was that the spectra of comets, the things that tell us about the composition, were all relatively similar. There was different amounts of dust, but we saw sort of the same species from one to the other. So back in the 70s, several of us started looking at what was the detailed composition. Were all of them the same, or were there some differences? And Micah Hearn, who will speak later, and myself, and Hy Spinrad at Lick and Ray Newburn at JPL all started looking at this, and we realized there were really two groups of comets. There were what we call normal comets. We're very creative with our names. And that represents about 70% of the comets. And then there were 30% of the comets that looked subtly different. They seemed to be depleted in long carbon chain molecules. Now, what is this telling us about the differences? Well, we have these two different reservoirs. We have the Kuiper Belt and the Oort cloud. Were those some of them from the Kuiper Belt and some from the Oort cloud? Unfortunately, science is never simple. Most of the depleted comets are from the Kuiper Belt, but not all of them, and not all of the comets from the Kuiper Belt are depleted. So that's still one of the questions that we really have, and one of the reasons we want to understand the chemistry of comets, because if they were formed in different regions of the solar system, and if we have different chemistries, those are important clues to the conditions of the early solar nebula. Well, the first mission to a comet was the ICE spacecraft. That was actually a spacecraft doing something else, and Bob Farquhar, who will talk after me, will tell you how he thought about redirecting the spacecraft so we could go to Comet Jacobini-Zinner. So I'm not going to talk much about that one. Left out a slide. This shows you the structure of the outer solar system. The plane of the ecliptic is that disk going across the center, and you can see that we have the Kuiper Belt in the middle, and then the Oort cloud is a halo of material going around it. So getting back to missions, the first mission that brought back an image of a comet there were 5 missions that went to Comet Halley in 1986. They were Giotto, which was a European Space Agency mission, 2 missions from the Soviet Union, Vega 1 and Vega 2, and 2 missions from Japan, Susi and Sagagaki. The one that got the closest was the Giotto mission from the European Space Agency. Now, that comet was going about 70 kilometers a second past the comet because the comet, as I said, was going in the reverse direction from the Earth around the sun. Now, if you're like me, you don't exactly intuit how fast that is. I live in Texas, and if I were to leave Austin, headed for Dallas, which is 180 miles away, going 70 kilometers a second, I'd be there in less than 3 seconds, and that's pretty fast. Now, imagine getting hit by a grain of sand, what that would do to your car windshield. Well, that spacecraft was hit by a grain of sand after this picture was taken, and it caused the spacecraft to start to tumble. But not before we got these first images that turned out to be very, very critical. This is a nucleus that's about 16 kilometers by 8 kilometers by 8 kilometers. You can see it's very irregular in shape. There's some structure to it. There's this bright stuff coming off of it. Those are jets. That's the beginning of the formation of the coma. We thought that comets, because they would ice, would be bright, but it turns out no. They only reflect about 4% of the light that gets to them, and that was a bit of a surprise that only a spacecraft mission would really tell us. The spacecraft was actually targeted on the brightest object, and had it actually succeeded in getting to closest approach, it would have been imaging the jets and not the nucleus, which would have been unfortunate. We learned that the shape is extremely irregular. We learned for the first time the size, which they're much smaller than we thought they were, but bigger than they would have been if they'd been really bright. We discovered that Fred Whipple was actually correct. They are dirty snowballs. And it was the Giotto mission with its mass spectrometers that first measured the fact that about 80% of the ice was water. Now, we thought that was the way it was going to be, but that was the confirmation of what we had believed. So this was a critical mission in our understanding of what comets look like. But obviously, these aren't the best images. It was 1986 after all, and comets and cameras on spacecraft weren't as sophisticated. We were flying extremely quickly past it and didn't know what to expect. So NASA had a mission called the Deep Space One mission, which was actually a technology demonstration mission trying to demonstrate solar electric propulsion, and it was going to go past a Comet Borreli. And this is the image that they took, and it looks very different. You don't see obvious jets coming off of it. It's very, very elongated. This is probably the most elongated object we know. It's alternately called the bowling club or the foot. It rotates around the narrowest point, which is not an impossible thing, but not necessarily what we would have thought of. And it has a jet going right off the pole, which was a little bit of a surprise. Only a very small part of the surface is active. You can see that it varies in color and shape, color at various places, and has smoother and less smooth regions. The variation in the darkness and lightness is actually exaggerated in this picture. It's still, the brightest part is only reflecting about 5% of the light that impinges upon it. What we were also able to do with not so much the spacecraft images, but because this comet has now a known pole orientation, and we know there's a jet coming off this pole, we were able to look at the jet forces on the orbit of the comet and derive a density and confirm that this comet is extremely low density. If you had an ice cube, solid ice cube from Earth, you'd have a density of 1 gram per centimeter cubed. Well, this comet has a density that's probably half of that. So that tells us if it's ice and dirt is actually more dense than water, that there must be lots of open regions. There must be lots of porous material. We also see smooth features in this, and those were a mystery what those could be. Probably ice flows, but we didn't know a lot about it. Well, meanwhile, there was another mission going, Stardust, and that was a mission to go past a comet, Wild 2, and bring back samples which were then landed in Utah and brought into the lab at Johnson Space Center, and laboratories around the world have analyzed the dust brought back from it. It's just dust collected. Now, first of all, they took pictures. You always got to take pictures. And looking at this, it looks very different from Comet Borreli. It's round, or more or less round. It also has these nice dimples in it, soft craters. One of them is labeled right foot. This was something that, again, didn't show lots of jet structure. It was small. It was even smaller than the previous ones we looked at. But we were able to collect bits of dust in a composition called aerogel, a catcher called aerogel, and bring those back, landed them in Utah in 2006, and those are being analyzed at labs all over the world. Now, this is a montage of images, and if you stretch the images, in other words, increase the contrast, you can see in that bottom middle picture that there really are jets, but they are very, very faint jets. And that's one of the things we've learned with this mission. Not only do all comets look different, but very little of the surface is active. When we see a comet like Comet Hale-Bopp or Comet West, we think that every bit of it must be putting out material. But when we look at comets, these little comets, we find that very little of their surface is active. And so something has sealed them over, probably the dirt that has fallen back upon the surface. Now, that in itself is an interesting question. Why are some comets very active and some comets less active? And Mike Ahern will talk about the epoxy mission coming up, and it's going to a comet that's as small as Wild 2, but is very, very active, or we think it is. We'll find out. With Wild 2, we find that the craters are very soft and weathered, and that's kind of what we would expect out of craters that are caused by outflowing material. And I'll get back to the point about craters being soft when I get to the next mission. I mentioned that we have samples in the lab, and those samples have been very important to understanding the materials. We find that the materials are chemically heterogeneous, so they're mixed up. Some of the particles show that they've been in very high temperatures. I said comets formed in the outer solar system, but some of the material must have formed close to the sun. So there's been a lot of mixing in the solar system that we learn about by looking at comets. Different fragments show very different chemistries. Some of the material has been identified as coming from prior to the solar nebula forming. Some of those grains are simple and single, others are fluffy aggregates, and some of them are missing any evidence of water, so that's pretty interesting. And as I mentioned, there are crystalline phases and there are amorphous phases. Okay, so the next mission was Deep Impact. July 4th, 2005, we had fireworks. This mission, which Mike will talk more about, 2 spacecraft, one being carried by the other. The little guy was put in the way of Comet Tempel 1, and Tempel 1 ran into it. The spacecraft didn't survive, or, well, it might have. It's embedded well in. And the flyby spacecraft took images as it went past. And this is an image of the comet. And doesn't look very much like a comet. It looks like a rocky body. You see there's an arrow coming from the left pointing to a smooth region. Everybody's first reaction was, oh, well, that's a low spot, and it filled in from icy slush, and it's a flow. No, it's a high spot. It's a scarp, and that's pretty unusual. Right above the arrow on the bottom left, which is where the impact crater would be if it could be seen, is a very sharp crater. I remember I talked about in Wild 2 there was these round features. Well, the craters on Tempel 1, some of them are extremely sharp. We would have said those were impact craters. But we know that as the comet sublimes, it pulls off material and shouldn't leave behind sharp craters. So we're eagerly waiting for Stardust next to go by and tell us what the crater that Deep Impact made looks like. And Joe Verka will talk about that. In this image, you see some colored regions. These blue colored regions, this was taken with an infrared spectrograph. Those are the regions that show ice on the surface. So even though I told you that the comet is a dirty snowball, we see almost no regions that we can attribute to ice. So only small regions of the surface are icy. So in the near future, we have 2 missions coming up, which will be talked about by both Mike and Joe. Mike Hearn's going to tell you about EPOXI, which is the deep impact spacecraft, which is being retargeted to Comet Hartley 2, and that flyby will be on November 4th of this year. Then Joe Vaverka will talk about the Stardust Next spacecraft, which is a return to Temple 1, and one of the things they want to do is search for the crater. All of these things tell us about the pieces of the comet. Are they agglomerations of big blocks that we can identify? How much structure do we have? The material that came off when the impact occurred was extremely low density. It was very, very fine, like talcum powder, although it was ice. The chemistry looked the same all the way through. What is this telling us about the origins of our solar system? And then there's another mission on its way, which is already on its way and will get there in 2014, and that's a European Space Agency mission called Rosetta, which will have a little lander, that's the guy on the top, called Philae, and it has a full instrument suite, and it will be the next mission that will tell us about the chemistry because it has a mass spectrometer aboard. So what do we still need to know? What are we trying to understand? Because if we want to understand the origins of our solar system, we need to know more about comets. We still need to know their mass. Nobody has measured the mass yet of a comet because on these fast flybys, you just don't get enough gravitational influence. These are little guys. We haven't really pinned down the density. We have factors of many in our understanding. We want to know, are comets rubble piles or are they assemblages of bigger building blocks? We want to understand the detailed chemistry, the comparison of the typical comets and the depleted comets and find out, are those chemically very similar or are there really structural differences? We would like to be able to measure species that you can't measure with ground-based observations. We want to look at how the morphology of the comet changes during an orbital passage. So Stardust Next will go past Comet Tempel 1, one orbit after the impact, and we will be able to tell not only is there a crater we can find, but what else has changed in the comet? Is that crater that was so sharp still there? Is that scarp that we see changed at all? How do things change with time? We want to know why some comets are active over so little of their surface and others over most of their surface. So going to Hartley 2, what's it going to look like? Is it going to be dramatically different? Is it going to have stuff coming out all over? Or is it going to be the same? And what drives the activity? What causes those jets to come off? Do they come off out of little crevices? Do they come off out of an impact area? Do they come off out of soft cones of material, soft regions of material? So all of those things are things that we will answer in the next 4 or 5 years, and with many missions hopefully in the future. We hope sometime in NASA's future we will actually even bring back samples of the icy portions as ice to tell us about the structure of the comet nucleus. And I think that's about it. So any questions? Okay. Regenerate in what sense? Build up?
Actually, as they go back to maybe some point deep in space, they might actually get bigger or add to them?
No. At this point, the solar system does not have the leftover debris that would allow them to add material. Now, some of the material that hasn't succeeded in fully getting away will fall back on the surface. Mostly that's the dirt part, and that dirt part will actually end up sealing up some of it, and that's part of the explanation of why they're not entirely active.
Oh,
Does anyone have any idea as to what the original population of comets might have been at the beginning of the solar system? If they're disappearing, the ones that we've seen, about 1,000 a year.
Right.
Do we have any idea what the original population might have been?
Well, we believe that what is left of the population is 10% of the original, and it's probably 100,000 billion right now, so 100 times that. It's a lot. But that's the ones that were not already incorporated into the planets. Now, a large fraction of them had to have been incorporated into the planets. So there was a lot of material. Yeah.
Is there any speculation on why there's so much water concentration in the comets? The water tends to be a pretty rare and precious element in the universe, and it's kind of fascinating that it exists in some of these ice balls.
Yeah, well, the most dominant material in the universe is hydrogen. And hydrogen will bond to lots of things. Oxygen is also pretty common. So when you're at the right temperature, you get water out of it. It's a pretty common thing to hydrogenate any material, and so you get water out of it. Now, it turns out that the point in the solar system where water ice can be stable is out past Jupiter's orbit. And we call that the snow line, basically. And so as the sun formed and the material in the solar nebula started to cool, it was natural that the outer part of the solar system, the planetesimals that were left over were the comets, and in the inner part it was the rocky bodies and it was the asteroids.
Thank you, Dr. Cochran. Now, ladies and gentlemen, we're going to change the format here. First, we're going to have Dr. Green turn into a TV host. And it's important that we do it this way because the next individual that is coming up, to really put things in context with his incredible history and accomplishments, we have to do it in a talk show setting, because the personal stories make even the history come out live and living color. And this individual that will be joining Jim is Dr. Robert Farquhar. He's executive for space exploration at Kinetics Incorporated in Tempe, Arizona. His PhD from Stanford, master's from engineering at UCLA, and his BS from University of Illinois. He has an incredible history of comets spanning the 25 years that we've been talking about here. So we're going to set the stage. They're going to join here up on the coffee table, and this is live television, so I have to warn you guys about Dr. Farquhar. He's a jokester. So he was entertaining us all morning. So Bob, keep it clean, live television. But ladies and gentlemen, it is an honor that I'm talking with him, and just listen to his stories. And please welcome Dr. Jim Green and Dr. Robert Farquhar.
All right, sit on your couch.
Well, thank you very much. Thank you, Duane. We'll see if I can come up with any good jokes. I'm not sure about that.
It's the stories we want.
Oh, okay, we want stories.
We can do the stories.
Are you going to, we haven't really rehearsed this very well, so this is kind of ad lib, but you'll get the general idea. I have a nice presentation that I was having for a seminar setting, but that's not what we have here. So we'll have to wing it a little bit and figure it out.
So let's start at the beginning, in the sense that you'd been at UCLA. You'd been studying orbit dynamics, and you'd written an interesting thesis that's really set the stage for your life and a lot of our future missions. Why don't you tell us a little bit about that, Bob?
Well, that was a terrible thesis, actually. I'm not proud of it at all. But it did give me my master's degree from UCLA. That was about preliminary considerations for placing a spacecraft at a libration point. Okay, then...
But what's a libration point?
well, I'm not going to talk about that yet. We're not
right.
there yet. You're getting way ahead of my story. But let's see, I was working on that thesis while I was at Marshall Space Flight Center in 1960. I was supposed to be working on the first stage of the Saturn V rocket. And I worked for a couple of days on that, but most of the time I worked on my thesis, and I did get it done, so that was a good thing. That was my start in libration points, and later on I went to Stanford, and I did a PhD thesis on the control and use of libration point satellites. So my big goal in life was to do the first mission to a libration point. So that's the thing. I was really motivated by trying to do that before anybody else. And around 1970, I was transferred to Goddard Space Flight Center. And I was only there for about a month, and they said, Bob, we need you to go to this study team meeting. It's in the Explorer project. And I didn't really want to go there, but I had to. Sometimes I have to do what the management tells me. So,
But that's been rare in your history, I know.
pretty rare, yes. Anyway, I went to the meeting, and they were talking about some 3 spacecraft program they were going to do in the future. 2 of the spacecraft are going to be in the magnetosphere of the Earth, making fine-scale measurements of the interaction with the solar wind. And then there was a 3rd spacecraft, an interplanetary spacecraft that was going to be measuring the ambient solar wind. And I sat there for a little bit, and they said that, well, this will be either leading or lagging the Earth in its orbit. And I said, wait a minute, this isn't going to work. What you've got here, it's impossible to put this thing at the edge of the sphere of influence. It's going to cost too much fuel. And they looked around, who is this guy? Where did he come from out of left field? You know, he's telling us what to do. Not only that, then I said, but I've got a better place to put it. You can put it at a libration point in front of the Earth, where you measure the input of the solar wind before it hits the magnetosphere. And well, of course, they were getting pretty irritated with me at that point. But I showed them this diagram, which we have up on the screen, I believe.
Yeah.
And what the libration points, for every isolated 2-body system in the solar system, such as the Earth and the Moon, there are 5 of these equilibrium points that I call libration points. And if you put a spacecraft there with just the right velocity, it will stay in the constant configuration with the 2 main bodies that are orbiting each other, such as the Earth and Moon that are shown in this diagram. There are 3 collinear points, and all of these points are unstable. So if you put a spacecraft there exactly at the right place, it'll stay there for a little while. But if you deviate the very slightest, it'll leave that area. But at the equilateral triangle points, the L4 and L5, it will stay there most of the time. It'll oscillate around. Well, the thing I was interested in was the collinear points of the Sun-Earth system, and they're also close to the Earth, about 1.5 million kilometers away from the Earth. Now this shows where they are. They're on the Sun-Earth line, and I wanted to put this interplanetary spacecraft at the Sun-Earth L1 point, where it would be able to measure the solar wind about 40 minutes before it got to the Earth. So then we could measure the solar wind input and then see what the reaction was with the other 2 spacecraft that were in the magnetosphere. So that seemed like a good idea. But then someone had said, they were already irritated with me because I interrupted their whole study and telling them that there's a better way to do things, and they didn't even know who I was. They said, well, wait a minute, you can't put something right at the Sun-Earth L1 point, because then you're going to be looking right into the sun. And how are we going to get any information back from the spacecraft? Because there's a lot of noise there.
It will swamp the signal.
Yes. And I says, well, I can take care of that, because if you oscillate back and forth normal to or perpendicular to the Sun-Earth line, it'll only pass in front of the sun once in a while. Yes, but we have a spacecraft that doesn't have any data storage on it. So that's no good. You can't go across the sun at all. So you can also oscillate out of the plane, and you can get into what I called a halo orbit, which I'd worked on in my thesis. And let's show the next slide. And you can see what this orbit looks like. This is to scale the figure in the bottom. And then the figure in the upper left-hand corner is the view from the Earth. In the center there's a zone of solar interference, and much larger than the diameter of the sun as seen from the Earth. That only subtends an angle of about 1/2 degree, whereas this is about 6 degrees, so it's pretty large. But if you have something in this orbit, it takes 6 months to go around this orbit. It isn't really an orbit, it's really oscillating around the libration point, oscillating in the plane and out of the plane. So that viewing it from the Earth, the spacecraft never gets in the line with the sun and you're able to communicate with it or get all the data back from it.
But you still had some problems with that, in the sense that it needed to be sold to the scientist.
Oh, yeah. Well, they didn't like this at all. As a matter of fact, people say, yeah, well, this is a nice theory, but we're talking about a real mission here. And how are you going to keep something? This orbit is not stable. And so if your orbit determination isn't very good, where does the spacecraft go? Well, it goes either in orbit around the sun or it comes back to the Earth. Well, they didn't like that very much. And so I kept trying to sell the idea to the project. But the project scientist, I dare to mention his name, I hope he's not watching.
He probably is.
Keith Ogilvy at Goddard Space Flight Center said, no, I don't want the interplanetary spacecraft to go there. And he's the project scientist. Sure. How could I argue with him? You know, and he just wasn't going to do it. I tried for over a year to convince him, but I was getting nowhere. So
in the meantime, the mission's proceeding.
Well,
it was called the International Sun-Earth Explorer, and they named the satellites IC-1, IC-2, and IC-3.
Right.
So IC-3, where were you going to put it?
Well, I wanted to put it in the halo orbit, but people said, well, that's a nice theoretical concept, but how do we know that's going to work? And Keith Ogilvy didn't want it there in any case. And so I thought, well, how am I going to beat this situation? So I resorted to my usual tactic, which is an end run. And so I went to Keith Ogilvy's boss, Norman Ness, who's the head of the Laboratory for Extraterrestrial Physics. And I explained the thing to him, and he listened very patiently to me, and he agreed from a scientific point of view, you would rather have it out between the sun and the Earth so that you measure the input function of the solar wind very close to the magnetosphere of the Earth. Mm-hmm. So that all made sense to him, but I had to convince him also that this thing was a practical concept, and I talked to him for a while, and somehow he figured that I knew what I was talking about. I don't know how, but he overruled Keith Ogilvy pretty well, and then the thing was pretty much on target, and we were going to launch the spacecraft in 1978 and fulfill my lifelong ambition to do the first libration point satellite. I remember calling home and telling my wife at the time that, I finally sold the Halo satellite. We're going to do it. Didn't just write a thesis, but we're really going to do this. But then Norman Ness came up with another idea. He had an idea to do a low-cost explorer spacecraft going to a comet. And he formed a comet study team, and he wanted me to come in there and do some of the mission design for it. And I thought, I don't want to do this now. I don't know anything about comets. And I want to do the first libration point spacecraft. Now, this is a distraction. So I went to the first meeting. I really didn't want to go at all. But after the first meeting, I found out a lot about comets, and I thought, these things are really cool. Now I wanted to do the first comet mission as much as I wanted to do the first libration point mission. So that was a good thing. Next slide, please. Here we see Norman and I working on the comet missions in 1972. We actually wrote a paper that year on a low-cost mission to a comet, a couple of them. This is Norman and I in earlier days. Now Norman is in the audience right out there. Raise your hand, Norman, and we'll put you on the camera. He looks a little bit like this guy here. He had darker glasses in those days.
Well, of course, Norm had a tremendous scientific body of work that he'd accomplished during that time. Planetary magnetospheres, made measurements at Mercury and many of the other planets, and done some really groundbreaking work in the Earth's magnetosphere on top of that. So you had a really solid scientist helping you in that, and that made a big difference.
Oh, that made a huge difference. And he introduced me to comets. If he hadn't had me come to that meeting, that study team meeting, I never would have really thought about doing missions to comets. So that was a big help. Let's see, next view graph. I'm not sure. Oh,
I see.
This is the IC-3 spacecraft. And it's not a very big spacecraft, about 1 3/4 meters in diameter and about 1.6 meters high. But actually, that's a little deceiving because it's a lot bigger than that. We have wires going out of it. It's spin-stabilized spacecraft. And as it's spinning around, the wires are going out 92 meters tip to tip. So it's actually pretty big if you look at it from that point of view. Had a lot of instruments on it, 13 experiments, mostly plasma physics, high energy particles and fields.
Magnetometer.
There was a magnetometer which you see on the one boom. That was from one of my favorite scientists on here, Ed Smith at JPL. He's still working at JPL. And then on the other end of the opposite to the magnetometer on the other boom was the plasma wave experiment from Fred Scarf. And so there was also a lot of hydrazine fuel on here, much more fuel than we really needed to do the basic mission, because I thought, well, if I put a lot of fuel on there, I might think of some other things that we can do with this spacecraft. Now, and ever since this time, people know now that I hog a lot of extra fuel, and it has a lot of extra delta V capability, so I'm known as a delta V hog. Ever since then, I can't shake this reputation, so people never believe any of my numbers when I tell them how much fuel.
It has served you well.
It's worked out so far.
Yeah. Now, IC3 didn't have an imager on it. Indeed, it was
Right.
plasma wave
Right.
measurements looking at the solar wind. So what about the launch? What happens next?
Okay, let me see what the next slide is here. Oh, well, here's a picture of the spacecraft. Now you get a better idea of the size. This is my late wife, Bonnie, on the right, and our daughter, Patty, in the middle, and I'm on the left. And this is when the spacecraft was having its in the magnetic test facility at Goddard Space Flight Center. So we got our picture taken in front of it. And then we were getting ready for the launch. This was 1978. And on the next slide, I think they show the launch. Yes, here it is. This is on Delta 144 on August the 12th, 1978. And I wanted to have my thesis advisor at the launch, and the project manager says, yes, absolutely, we'd like to have him at the launch, because there was still a lot of skepticism as to whether this was really going to work. And so they wanted him to be at the launch and to bring a copy of my thesis with him. And if it didn't work properly the way I said it was, then they were going to have him revoke my doctor's degree. Fortunately, it worked, and he didn't have to do that. Next slide, please. Okay, this is just a picture of the transfer from the Earth orbit out to the halo orbit. And it took about 100 days to get out there, and we inserted into the orbit on November 20th, 1978. And it takes 6 months to make every one of these circuits of the halo orbit. Everything worked quite well for a long time. And we were in this orbit for a couple of years, and I was getting bored with all the operations. That's 4 of these orbits around the libration point. And even prior to the launch, I had talked to Fred Scarf about trying to do something else. Couldn't we send this out into the tail of the Earth, beyond the moon? No one has made any measurements out there. This is the Earth's plasma tail.
To the other libration point.
Yeah, but didn't care about the libration point.
All right.
Wanted to go into the geotail area.
Right.
And you know all about that. You're a plasma physicist, right?
Right.
And why is that important, the solar-wind interaction with the...
That's where they believe the aurora really starts, from a reconnection that occurs in the tail. Field lines from the north to the south then come together. Particles are accelerated to the Earth and then rains on our upper atmosphere, creating the aurora. And of course, the IC mission, the two inside, were making fabulous discoveries because they could make that measurement in the solar wind and see the effect in the magnetosphere. So the set of three was doing a fabulous job. And so the scientists were, I'm sure, very delighted your idea worked out.
Well, they were very happy to have it in the halo orbit, but they didn't want to move it back into the tail.
Because of all the discoveries that were coming out from that relationship.
But Fred Scarf wanted the spacecraft to go back out into the tail. He wanted to do something different. And so he arranged a meeting with the science team, and we took a vote and everything, and they were split pretty much 50-50 on whether to send it back in the tail or not. Finally, we convinced them to let it go back. Okay, you can have one pass in the tail, but then we want to put back into the halo orbit.
Get back to where it was.
And we want to keep doing that stuff. This wasn't going to happen for a couple more years yet anyway. So they thought, well, they'll get 4 years in the halo orbit before we have to divert the spacecraft in any way. But then other things were going on at the same time. In 1981, there were a lot of spacecraft going out to Halley's Comet, and everybody was very interested in this. And the United States was interested in doing a mission to Halley's Comet also. And I was even sent down to headquarters to be the program manager for the Halley's Comet mission. And JPL was going to do it, but they had something that was going to cost a little too much, and we ended up not doing anything, but the Japanese and the Russians and the Europeans all sent spacecraft to Halley's Comet. So one day in late 1981, Fred Scarf called me up. He said, Bob, you said that we might be able to send IC3 out to Halley's Comet by using the gravity field of the moon and slinging it out there. I said, yeah, I think we can do that, but Halley's Comets, any encounter with that would be too far from the Earth, and we really can't get very much data back, almost nothing. But there's other comets that are a lot closer. Maybe we could try to do that. Well, Fred Scarf was all for that. And we brought that up with the IC science team. Oh, no way, no how.
Yeah, right.
No way, no how. You're not going to steal our spacecraft from the halo orbit. We want to keep it there. We'll let you go back in the tail, you come back out to the halo orbit, and that's going to be it. Well, no, we want to send it. We want the United States to have a Comet mission too. And besides, I was motivated by the fact that we'd get to this other comet about 6 months before everybody else got to Halley's Comet, so this would be the first Comet mission. Right. We didn't have a camera, but we could do a lot of good things with the solar wind interaction. So the science team would not budge. They were not going to do it. They voted against it, and there's no way you can ever change something like that.
So what are you going to do about that, Bob?
Well, then what we're going to do is make another end run.
That's right.
And Fred Scarf was just the right guy, and we also got the magnetometer, the principal investigator for the magnetometer instrument, Ed Smith from JPL. The two of them were my champions, and we set up a meeting with the National Academy of Sciences. And we managed to get them to agree that this was a better idea than putting it back in the halo. Of course, the scientists weren't happy about that. Now, there was one other problem we had, though. Even though we were getting somewhere with the National Academy of Sciences, we still had to get NASA headquarters to okay the whole thing. And we had a more serious problem, and that is I hadn't really worked out all the details of how I was going to transfer the spacecraft from the halo orbit back in the tail and then out to the comet. And the comet we were going to go to was something called Jacobini-Zinner. And I think a picture of that is on the next, no, this is Fred Scarf. This is my buddy Fred Scarf, who helped me make this end run.
Yeah. Also another fabulous planetary scientist and been on a number of missions in plasma waves, and was a real pioneer.
Yeah, I really miss Fred.
Yeah.
But fortunately, he lived to see the actual comet encounter, and several years afterwards published all kinds of papers on
Yes, he
it. So
did.
that was all good. But as I was saying, we still didn't know how to get there.
But in theory, you figured it would work, right? Just
Well,
like your thesis and.
I knew that we could use a lunar swing by that would give us enough energy to get out there, but we had to get there at exactly the right time, the right angle, and everything had to be just perfect.
Yeah.
And we were already in an orbit around the Earth and out in the halo orbit as well. And how were we going to do that? And we had to do it in a very short time. Next slide, please. Oh, this is a picture of Giacobini's inner, and you see it has a nice ion tail going out,
Right.
which is unusual for the shorter period comets. And this helped us sell the thing a little bit because it did have this nice tail. It didn't look like a blob.
But the idea, because it was didn't have an imager, that it made measurements of the solar wind and the plasma interactions that indeed from the very beginning you had planned to go through the tail.
Yes. Oh, yeah, definitely. Yeah, that was the only way we could do it. And we were going to get there at the time it crossed the ecliptic plane because that was the lowest energy way to intercept the comet. And I wanted to get there on my birthday, which was September the 12th, but September 11th was the optimal time, so I couldn't change it.
You did
I
make
tried-
a compromise.
I tried to, yeah. I don't always do this.
You don't. Yes,
No.
you don't.
Okay, next slide, please. Now this is too complicated, but the idea is that we knew pretty much when we had to hit the comet. So working with my colleague David Dunham, who's in the audience out there. There he is. Hi, Dave. We worked on this thing for many, many months, and what we had to do was take the orbit that we were in, and we knew we had to use the moon to shape things just right. So we had to use passes of the moon, use its gravity to shape the flight path. So we would get to the moon on the final time when we wanted to launch out to the comet at the right time and everything. And we thought this, well, it's going to take a little work, but we knew the beginning of the flight path and the end, but it's like digging a tunnel through a mountain from both sides and hoping you're going to meet in the middle, and you're not sure. And we kept going this way as we calculated things, and then, no, this wasn't going to work. We worked on it for about 3 months trying to shotgun the thing.
But then you had this meeting at NASA headquarters, and
Well,
it had to be right.
We had to find it in time for that meeting, but we figured we had about 8 or 9 months. It shouldn't be any big problem. But we worked on it for about 3 months, and Dave really worked hard, trying all kinds of different things. But there's an infinite number of ways that you can do this, and we only did maybe a few thousand, tried a few thousand cases, and nothing worked. Well, I wasn't too concerned. Then we came up with a more systematic way, and we narrowed it down to about 100 possibilities. And I was pretty sure we would get the answer. And Dave, then we got down to one case that I was positive this was going to work. I said, Dave, here, try this, this, and this. And so Dave went away. He worked on the thing, came into my office one day, and had about 10 of the cases there. And we had to move the flight path through a certain angle. But none of the cases moved through that angle. I thought, wait a minute, this thing is not going to work. What am I going to do? We've already talked to the National Academy of Sciences. They said, go ahead and do this thing, and now we don't know how to do it.
Yeah, and you're going to ask
What am
NASA
I gonna
headquarters
what
for
am
the
I
money
gonna-
to pull it off.
What am I going to tell people? So I drove home that evening. I thought, oh, no, now I've done it. But then I got home, and Dave called me. There was another case, and we had overshot the area that we were trying to get to. So now we had it bracketed, so I figured in the end we would find the final solution, and we did. Barely. We had lots of people working on this thing at that time. We had, I don't know, 12 or 15 people, and they were integrating the flight path out, and it took them about 2 weeks to go through each case. And this is a very complicated thing because we're operating at the edge of the sphere of influence of the Earth, so we're in, the whole flight path is very chaotic, so it's difficult to calculate these things. Can't use two-body formulas. But we did eventually find it, and this is the mission that we flew, and we did the first ever lunar gravity assists. And we flew by the moon 5 times to get to the comet. Well, for the first 4 times, we flew by the moon, and we flew quite far from the moon, about 20,000 kilometers each time. So management wasn't too worried about us. There were no reviews. Dave and I were just 2 guys working on our own. And I said, Dave, what do you think? We should go this way? Oh, no, let's just move it a little bit this way. Okay, that's fine. There's no reviews, nothing. It's not like things are done nowadays.
Yeah, gone are those days, I can tell you that.
How are they done nowadays?
Oh,
Maybe
you'd have been reviewed to death. You wouldn't have had time to do it.
Well, but then we got to the final lunar swing by, and all of a sudden the management realized that this one was going to be a lot closer than all the others. This was going to be 120 kilometers above the surface of the moon. What? They found out about it. Wait a minute, this is very close. What if something goes wrong? Next slide, please. And this shows just how close it did come to the lunar surface. And about a month before, someone doing the orbit determination wrote in the Goddard Weekly, they said, well, our latest orbit determination shows that the flight path is going about 200 kilometers under the surface of the moon. And then they also wrote down, this is in the Goddard Weekly that went to the director and so forth, it says, well, we can't be perfect all the time. Then everybody made fun of the fact that there was going to be a new feature on the moon, and they called it Farquhar's furrow.
You were going to dig a trench, that's right.
Yeah,
but what happens,
by.
of course, is that raises it to what we always call the level of deadly visibility. Now you've got reviews, but you'd already solved that problem.
Yeah, I wasn't really worried because we had another correction to make. It only took a very small correction, and we flew by perfectly at 120 kilometers, so it wasn't a big deal.
Yeah.
Then there were many other adventures on the way out to the comet, but we don't have time to talk about all that. And we eventually got to Comet Jacobini Zinner, and 6 months before everybody else. And Time magazine talked about us upstaging all the other people. And of course, I ate that up. That's what I like to do. And so we were able to do the first Libration Point mission and the first Comet mission. And the next slide, this is still showing us flying by the moon, and this is what it looked like. If you were sitting behind the spacecraft and the Earth is in the background, looking like a crescent moon here, but the moon is in the foreground. And in the next slide, here we are coming to the comet. This is a picture that we gave to Science News. And I just got permission from Science News. I can reproduce this picture now.
Okay, good.
Okay, so it's good that I did this before this meeting. And the next slide shows some of the details of the traverse through the tail. And this also shows the magnetic field measurements superimposed on this false color image of the comet. And you see we did a nice cross-section of the tail. And you can see the magnetic field measurements, and the direction is changing as we fly through the tail. And since you're a scientist that knows about this, you go ahead.
Well, you know, comets don't have an intrinsic magnetic field, but they're much different than a terrestrial planet with an atmosphere. It's sort of like a reverse. You know, instead of a big planet with a small atmosphere, a comet is a small object with a large neutral coma, which then gets ionized, and then a variety of plasma wave turbulence takes over. The material interacts with the solar wind, and an induced magnetic field arises from that. And this trajectory that you had created goes right through the tail. And this is now a fabulous set of observations. Our first, we can see as we go through the tail, the magnetic field directions reverse from the southern and the northern lobes, and we go through the center part called the plasma sheet, where the ion tail actually is being formed. And so being, seeing it from Earth and then actually going through it and understanding the physics of it, of course, has really got the magnetospheric community and plasma wave and solar wind community very excited. And of course, we've never done this again, all the other spacecraft or imagers have other types of instrumentation on it, and always went in the front side where they could actually see the comet itself. Going through the tail, you don't have that illumination.
We'll have to do another one like
Yeah,
this.
we'll have to, Bob. I'm sure that's in the works.
I'm going to get to this in a second.
Oh, okay. Yes, the discovery proposals are due today, by the way. That's right.
And Anita Cochran and I have a nice one. We just
I don't want to
gave
hear
you.
about it, Bob.
It's called Prime.
I don't want to hear about it, Bob.
Okay, I'm sorry. I'm sorry. Okay, I'm not supposed to do this. Let's see the next slide. Okay, notable accomplishments, yes. First spacecraft is stationed at a libration point, and this has paved the way for a lot of missions that have gone to libration points.
it has.
Like there's a spacecraft called SOHO that's looking at the sun from the European Space Agency. And
ACE is there.
ACE, yeah.
Wind is there.
yeah, and Genesis was there, MAP. And in 2014 or so, there's going to be the James Webb Space Telescope is going to the Sun-Earth L2 point. So now people don't feel like this is just some theoretical thing now, and the IC3 mission really showed them that this could be done.
That's
and
right.
It was practical, and it could be done for very little fuel, and it wasn't all that hard to do it. And we also did the first exploration of the distant geotail and the first comet encounter, so I liked all these things. We did 3 missions with 1 spacecraft. This is probably the most cost-effective mission that NASA has ever had, at least I say so. We did the extra 2 missions, and the surcharge to do the extra 2 missions was like $2 million. Very, very cheap.
Yeah. Well, of course, we're taking the page from that book. Both the next 2 speakers are going to talk about epoxy and Stardust Next, and both of those spacecraft have already completed their prime missions, but have enough fuel to go on and do some other special activities with comets.
It's good to do more than one thing and have extended missions.
Yes, it is.
But as I say on the last bullet here, what's next? What's next for the IC3 spacecraft?
Yeah, the story's not over.
Okay, let's see the next slide. Well, this shows the path of the spacecraft around the sun relative to a fixed Sun-Earth line. So the Earth and the sun are fixed in this diagram. And we have this looping motion because when it goes inside of the Earth's orbit, it's moving faster than the Earth. And when it comes outside of the Earth's orbit, you get this little loop, it's moving slower. So relative to the Earth, it seems to take this looping motion. And shortly after we flew by Giacobini-Zinner, I retargeted the spacecraft so that when it would come back to the Earth in August the 10th of 2014, and it would come by close to the moon so we could recapture it in an Earth orbit. NASA decided that it had done enough operations in 1997, and they terminated the operations on the spacecraft. Well, I didn't like that, but I couldn't say too much about it at the time. But then we tried again to contact it in 2008, and I talked to some people in the DSN to look for it, and sure enough, we found it was still working in 2008, and it's on its way back to the Earth. The next slide, please. We had thought about this 1 year after the encounter with the comet. We thought, well, if the spacecraft can come back to the Earth sometime, maybe we can recapture it in Earth orbit, bring it and use aerobraking to bring it down to a low Earth orbit and then pick it up with the space shuttle. So we had a little ceremony at the Air and Space Museum. And in this photograph, the second from the left there is the NASA administrator at the time, Jim Fletcher, and he signed a notice of intent with the Air and Space Museum to bring the spacecraft back to the Air and Space Museum if we recapture it with the space shuttle. So I'm still hoping that we can do something like that. And the final slide, the next one, shows us coming back, and here it is coming back to the moon in August 10th, 2014, doing a swing by of the moon. coming back, and then bringing it back into the halo orbit, because I have to put it in the halo orbit for a while because most of the scientists on the IC-3 mission felt that we stole the spacecraft from them, but we really didn't steal it. We just borrowed it for a while.
Keith will be happy.
For the 30. Yes, he's still working out at Goddard, and now he'll be happy.
He'll be happy. Yes,
he can do his thing again. But I'm planning to send it to another comet in 2018, and we'll have to use some more lunar swing-bys. But it's kind of easy to do. So that's what I'm working on right now. Hopefully we can do this.
All right. Well, Bob, it's just been delightful talking to you this morning, and we need to have some questions from the audience.
Is there time for questions?
Okay.
Oh, before you do that, there's one story that you didn't tell that I dearly love. And that is, okay, it might not be a dearly loved story, but you had a heart attack. And you ended up in the hospital.
Yeah, okay, I can tell this story.
All right.
Okay, yeah. Well, Dave and I were, I said we were working trying to find the solution. How were we going to use the swing-bys of the moon to get out to the comet? And there was no solution was coming up. So having nothing to do with that, I was playing basketball with my daughter, and around Thanksgiving time, it was cold outside, and I didn't feel right. And I found out I was getting a heart attack, so I had to go to the intensive care unit and everything. And I told my wife, I said, listen, bring my briefcase in here and everything, because I can't stop working on this thing. Dave and I have got to solve this problem. So I brought that in there, and I started talking about how, and they tried to stop me from doing this, but the doctor said, well, I won't be as stressed out if I bring all the work in with me. So they went along with that. But then a couple of days later, they had the psychologist at the hospital talk to me, because who's this crazy guy? He's talking about sending a spacecraft out to the moon, flying by the moon, and then sending it out to a comet. This guy is hallucinating. But I wasn't really. And they
Well,
found out
unfortunately, they did let you do that.
Yeah.
Thank you so much, Bob.
Okay. Thank you. Okay, well, we can get a drink here. Help me down.
Thank you all. And Bob, thank you for keeping it clean. I appreciate that. And Dr. Green, I have to tell you, after you finish your incredible work in science, you make a pretty good television host. Okay, well, I have to tell you, particularly to our folks watching NASA television across the country and via www.nasa.gov, I'm hearing in my ear that we have numerous classrooms watching the show, and for me, I want to be very clear that scientists are certainly incredibly smart and brilliant and do incredible work, but they are really a lot of fun to be around, and they're really cool. So those classrooms, your science teachers are really cool, okay? Remember that. Speaking of cool, our next speaker, Dr. Michael Ahern, principal investigator for the upcoming Comet encounter, which I mentioned coming up on November 4th. Dr. Ahern received his PhD in astronomy from the University of Wisconsin and is currently a distinguished university professor at the University of Maryland. And you probably know his name because he is the principal investigator for the Deep Impact mission, which incredible media coverage and just was just an awesome mission. So ladies and gentlemen, please welcome Dr. Michael Ahern.
Thank you, Duane. So I'm going to talk to you today a little bit about the Deep Impact mission. You already heard some of it from Anita, and how it turned into the epoxy mission. If I can make this work. The Deep Impact mission was actually 2 spacecraft, not 1. And you see a picture of it there, where it was the 2 spacecraft were being mated together in the clean room at Ball Aerospace. Ball built the entire spacecraft, the 2 of them. The lower one is the impactor, And that's the one that went into Comet Tempel 1 on the 4th of July in 2005. And the larger upper one is being lowered down to mate with the impactor nestled inside one end of the flyby spacecraft. So the flyby spacecraft is a little bit bigger than the people you see there, but not a lot bigger. The flyby spacecraft is still doing fine. The impactor spacecraft isn't really there. I should say that Bob Farquhar told you a lot about the ICE mission, the first mission to any comet. Deep Impact and Stardust that Joe Vaverka will be talking about shortly were the first two missions selected by NASA and flown specifically as comet missions. Stardust was selected in 1996, and Deep Impact was selected in 1998. The Deep Impact was meant to be the first planet-scale experiment on a comet. The impact had several aspects. Some people thought, before they saw what science came out, thought, oh, this is just a publicity stunt. The other people said, the BBC asked me in an interview once, how much of this is little boys wanting to throw things in a sandbox? And while there's a bit of that in it, we really were driven by the science, and I'll get back to that. But before I go on to talk a little bit about Deep Impact, I need to tell you about the name evolution, because a lot of people get confused by it. After Deep Impact was all over, Drake Deming of Goddard Space Flight Center and I wrote two entirely separate proposals to reuse the Deep Impact flyby spacecraft. Drake wanted to use it as an observatory to study extrasolar planets, and I wanted to use it to fly by another comet. NASA selected both proposals and said, put them together. So the extrasolar planet observation and characterization mission plus the Deep Impact extended investigation became EPOXY. And I'm only going to talk about the Dixie part. The EPIC part is all finished, and Drake Deming's team is writing lots of papers about the results from that. But I'll talk about the Dixie part that's going to Comet Hartley 2 on November 4th. We have two primary scientific goals of this mission. The first is to try to understand why comets are different by going to a much smaller comet. As Anita said, this is a very small comet, seems to be active over all its surface, unlike the other comets we've been to that are active only over a small part of their surface. We also want to try to understand many of the things we saw at Comet Tempel 1 during the prime mission and ask which of these features really are telling us about the origin of the solar system and which of them are telling us about more recent evolution of the comets. So those are the two goals of the mission. And Anita showed you some pictures from the prime mission. I'll show you a couple of movies. Think of yourself as running backwards as fast as you can and the comet coming down and hitting you on the head. That's roughly what's happening. You have to be running pretty fast because the comet's coming at you at about 10 kilometers per second. And you notice that the view from the comet is bouncing around. These images are taken by the impactor. The impactor weighs 1/3 of a ton. That image is bouncing around because that 1/3 of a ton spacecraft is being hit by dust particles that are roughly 1/100th of an ounce. When you get to these high encounter speeds, really tiny things can have a big effect. And you see we come down right in between those two big craters that Anita pointed out in one of her pictures. So, the impactor images stopped just before we hit. Actually, it kept on taking them, but the last one we got back. Here was the view from the flyby spacecraft. And you need to notice two things. There's a time scale on the lower left telling you the time from impact. Right at the time of impact, there's a really hot puff that goes really fast to the lower right corner. There it's gone already. That hot puff that went by is about a ton of material, 3 times the amount of material that went in, moving at about half the speed of the impact. Probably it contained part of the impactor. Some parts of the impactor evaporated. The rest of the impactor is probably molten metal buried 20 to 30 meters deep on the cometary nucleus. Probably most of it's still there. Most of it wouldn't vaporize, at least as we understand from our analogies with laboratory experiments. So Anita told you some of the things we found out. The impact was the key goal of the mission. And from that, we found out, for example, by a completely independent method, watching the debris fall back on the surface, that the gravity is very low and most of the inside of the comet has to be empty space. And as Anita told you, we found out that the material we dug up, going down 20 meters, had the same composition as what normally comes out right at the surface. That contradicts a lot of the theoretical models of what should be happening. And I think the answer is that although we predict that the dry ice, the frozen carbon dioxide, and the water ice should separate, the surface erodes fast enough, all the dust getting lifted up by the gas, it erodes fast enough so that the ices down below don't have time to separate. Now, that's not what most of the models predicted. So we found many results that contradict previous predictions. The very low density is a problem for putting comets together. You know, out in the Kuiper Belt that Anita talked about, we think things should come together at 1 or 2 kilometers per second. How do you bring things together at 1 or 2 kilometers per second, have them stick together, and still maintain that porosity? That's a challenge for the physicists, the theoreticians. So these are the kinds of things that we saw. And I want to say that here are the pictures of the 4 comets we've been to. The 3 pictures on the right are all printed at the same scale. So those 3 cometary nuclei are roughly all the same size. Comet Halley is a factor of a few bigger. The comet we are going to, Comet Hartley 2, is 5 times smaller. And we think it's active over all its surface. So by going to a much smaller comet and one that's much more active in terms of how much surface is active, we hope to understand why some of these apparent differences are there. Now, one of the important things I like to point out about deep impact is that although we proposed a mission to do an impact and see what happens, and measure the physical properties and chemical properties from that, only about half of the results from the mission came from the impact. The other half came from what I call the Harwood principle. Martin Harwood was a professor at Cornell, a director of the National Air and Space Museum. Wrote a book pointing out that you write a lot of science justification every time you want to do a big project in astronomy. And you look back 10 years after you did the project, and what do you remember it for? Not what you proposed it for, but because of all the unexpected discoveries. Because you went to a new place with a new technique, did a new kind of experiment, had much better spatial resolution, or you did something else unique and you've made unexpected discoveries. So that's an important principle, and at least half the results from deep impact came from that. So here are a few pictures from deep impact. The picture on the lower left points out the smooth areas that Anita talked about, and Joe Vaverka will talk more about that when he talks about stardust next, going back to Comet Tempel 1. Picture on the upper right shows the icy areas, and again, Joe will talk more about that. Right below that picture on the upper right are pictures of where the gas is coming out. The black spot in the center is where the nucleus has been removed. These were taken with our spectrometer, and the upper image is an image of where the water is coming out, and the bottom one is an image of where the carbon dioxide is coming out, the water ice and the dry ice. And you notice that the water ice is coming out mainly to the right. That's where it's noontime on the comet. Carbon dioxide has got a whole bunch coming out in the lower left. That's coming out the South Pole, where it's been in winter, permanent darkness for 2 months. Now, is this because of modern evolution, or is that telling us we brought together pieces of the comet from different parts of the solar nebula? Stardust discovered mixing of microscopic materials. Is this a sign of mixing of the really big stuff, the cometesimals that came together to make the nucleus? On the left, just in from the left, you see a picture with a bunch of yellow on it. There's a dark band going across the nucleus. That extends all the way back parallel to that upper surface. Some of us would like to interpret that as an original cometesimal where the last couple of pieces of the comet came together. You also see a bunch of jets in a picture to the right of that. Those jets aren't coming from the icy areas. All the models said we get jets in comets where you have exposed ice on the surface. Well, you do get really tiny jets from the exposed ice on the surface, but most of those jets aren't where there's any exposed ice. So why do we get jets? In the upper left, you see a graph that basically shows that Comet Tempel 1 had a random outburst roughly roughly twice a week. We've known for almost a century that comets have outbursts, but we never had the really continuous coverage to show how often and to show really small outbursts. These seem to be correlated with the orientation of the nucleus. They probably only come from a couple of areas on the nucleus, but outbursts twice a week were quite surprising. Don't know if that's common to all comets or not. So these are some of the results. Heterogeneity, ice is a little bit on the surface, but most of the water has to come from ice that's buried under the surface. That says the ice is very close to the surface. It's not buried very deeply. So we're going on to Comet Hartley 2, which is shown here. That's a picture from Lowell Observatory in July of this year. We have been en route. We've spent the last several years orbiting the sun, flying back by the Earth every 6 months. We studied the lunar hydration, the water on the moon, showed that it comes and goes every time the moon goes through a day. But now we're not coming back to the Earth again. We're off to the comet. And we just started observing the comet on this past Sunday. And here's a picture of the comet that we took from the spacecraft last Sunday. It's that fuzzy thing in the middle. Doesn't look very impressive, but that's a 10-inch telescope that's further from the comet than the Earth is from the comet. And the fuzz that you see around there, if you look carefully and play with the image, you can see that it extends at least 30 to 40,000 kilometers. So this comet is really active. There's plenty of stuff there for us to look at. As I say, that's an average of 7 images from the first day of observing. We've now got half a dozen days of observing of the comet, and already we're seeing brightness variations. Don't know whether we've seen an outburst or not, but we're certainly seeing variations. Right now, we can only look at the comet once every 6 hours, because if we look at the comet continuously, everything heats up too much. In another couple of weeks, the geometry will change and we'll be able to look at the comet almost continuously. But for the first 20 days of observing, we're only looking intermittently. So we are on our way to try to understand why comets are different from each other and which parts of them are really telling us about the origin of the solar system. Any questions?
Thank you, Dr. Ahern. Just 2 quick questions, if I may. The first, what is the approximate mass of the spacecraft?
The flyby spacecraft?
Yes.
It's about 2/3 of a ton.
Okay. And the second question is, can you explain what the difference is? I'm a layman in this area, but what's the difference between a non-active comet and a meteor?
Oh, a meteor is a phenomenon in the Earth's atmosphere. And when you see a meteor, mostly what you're seeing is the trail of ionized gas in the Earth's atmosphere that's made by the meteor moving through it. That's the primary thing you're seeing. You're seeing some glow from the meteor, and you may see fragments of the meteor break off. But those are solid particles that come into the Earth's atmosphere. Some of those particles come originally from comets, others come originally from asteroids.
How much mass would a typical comet lose on a single circuit of the sun? I mean, it has a finite body of water, ice, gases, and so forth.
Mm-hmm. Well, in the case of Comet Tempel 1, that's about 3 kilometers in radius. I mean, it's not a sphere, but on average, it's about 3-kilometer radius. And if you just look at how much material comes out as it goes around the sun, it has to lose somewhere between 1/3 and 1/2 a meter of material every time it goes around the sun, averaged over the whole surface.
Did the impactor on Deep Impact impart any measurable, discernible delta V to the comet itself, or was it just too small?
Yeah, we have done the calculation. It's not measurable. This is actually important for the issue of deflecting potential impactors on Earth. The change in speed of the nucleus should have been less than about a micron per second. If you do a crude estimate of how much it should have changed at the next perihelion passage, when Joe's going to go back and look again, it should be displaced from its original orbit by less than 100 meters, by less than the size of one of those craters on the surface. Totally unmeasurable. And the real thing is, it was a small impactor into a relatively large cometary nucleus. Not as large as Halley, but relatively large. And for the near-Earth object hazard issue, you're typically going to try and send as much mass as you can, and most of them are smaller than that.
Okay. Final speaker for today's program. He reminds me actually of one of my favorite professors while I was in school, Dr. Joe Farquhar. Received his PhD from Harvard, working under the mentorship of Fred Whipple, who was mentioned earlier today. And now Joe is professor at Cornell University. Ladies and gentlemen, please welcome Joe Farquhar.
Thank you, Duane, and good morning, everyone. I am up here this morning to tell you a little bit about the Stardust Next mission. And in fact, Stardust Next is the tale of two missions that you've already heard a little bit about, Deep Impact and the original Stardust mission. The original Stardust mission was launched in 1999, and the objective of the Stardust mission was to encounter Comet Borreli 2, collect dust from the coma of the comet, and return that dust for analysis on the Earth. And that happened successfully in January of 2004, when the Stardust spacecraft flew within something like 140 miles of the nucleus of Borreli 2, successfully collected dust, and then was on a trajectory that took the spacecraft back to the Earth. The spacecraft had the main body of the spacecraft and a capsule that contained the dust. And when the two of them got close to the Earth, the capsule separated and landed in the Utah desert in January 2006, containing all this precious dust from the coma that had been collected earlier. In the meantime, the main spacecraft stayed in orbit around the sun. Now, the dust that was brought back has been and continues to be analyzed in great detail. It continues to provide insights into not only how comets formed, but, as Anita mentioned, it provides important information about some of the physical and the chemical processes that were going on in the earliest phases of the nebula out of which the solar system formed 4.6 billion years ago. So the original part of the Stardust mission was accomplished, but still there was this wonderful spacecraft left in orbit around the sun, which is in perfectly good shape, working very well. And so in 2006, some of us decided to propose to NASA that we could use the spacecraft to explore some more about comets. And this proposal was accepted by NASA in 2007, and so that was the beginning of the Stardust Next mission, next standing for the next exploration of Tempel 1. Because yes, indeed, the comet we are going back to is Micah Hearn's comet, Tempel 1. And so one of the questions you might want to ask is, given the great success that Deep Impact had in visiting Tempel 1, why in the world would you want to go back there again? And I think there are important reasons. So let me just sort of tell you some of them. Probably the most obvious and simplest one comes from just looking at one of the Deep Impact pictures of Tempel 1. This is an amazing comet. It has tremendous geologic diversity on the surface. If you look carefully near the bottom of the picture, you will see some very heavily eroded terrain, places where ices have sublimated and left the comet. A little bit higher up, you see some very smooth areas, areas that look very much as if material erupted from the subsurface and flowed across the surface, leaving a very, very smooth deposit. If you go a little bit higher up in the picture, you will actually see layers in the structure of the comet. I should say that in this particular rendition, this is a false color image, and the blue areas that you see are the few areas on the surface where water ice is actually exposed. Otherwise, this is a very dark, almost black surface, and those blue areas, the few places where you actually can see water ice. So it's a very, very amazing comet geologically, and to sort of make that point a little bit more clear, I'm going to show you a geologic map of the comet. This is what geologists like to do, where you basically look at the morphology of the surface, the kinds of things that you see, and assign different colors to things that look different. And so in this view, for example, the heavily eroded terrains are shown in orange. The smooth flows, there are two of them in this view, are shown in yellow. And what you see in green are the areas of layered terrains. So this is very, very interesting, and obviously we would like to learn more, because Deep Impact during its flyby only saw about a third of the surface of the comet. So what we would very much like to do is, for example, to have a better look at these layered terrains, which are shown in this picture near the top. How extensive are these terrains? Are they global in extent? What do they tell us about how the comet was actually put together? Those are important questions, and by seeing more of the surface, we can perhaps answer some of those. Similarly, we have questions about these smooth flows that I mentioned, places where it really does seem that a fluid came from the subsurface and deposited material downhill on the surface. Deep Impact saw about a third of the surface, saw about 2 of these kinds of flows. Are there more on this nucleus? But the main reason why we really want to go back to Temple is to do something that has never been done before. We've heard several times this morning that when a comet approaches the sun, the surface heats up, ices evaporate, the surface changes. Okay? But we've never seen this happen. Here we have an opportunity to go to a comet that was previously observed in 2005 by Deep Impact, look at the surface 1 comet year later in 2011, when the comet's coming back to the sun again, and see where the changes have occurred. We've heard this morning that for a comet like Temple, on average, the amount of ice that's lost during 1 orbit around the sun is roughly about a foot or so, or maybe a little bit more. But that loss does not occur uniformly over the surface. We suspect that it's concentrated in certain areas. So there are places that lose much more ice than other places. We'd like to know, where does this occur? Does this occur, for example, in that heavily eroded terrain on the bottom of the picture? Does it occur in the smooth areas? Right now, we don't know. And one of our major objectives, the single major objective for our mission, is to go back to Temple 1 comet year later, and see what has happened to the surface. Where has the surface changed, and by how much? And that will be an important step in actually figuring out how comets work. So that's really what we're after. Now, to achieve our objectives, we really have 2 different things I talked about. We talked about wanting to look at the places that had already been seen by Deep Impact, to look for the changes. But we also talked about exploring some more of the surface, the part that wasn't seen by Deep Impact. So we have 2 things that we have to balance. And what this little sketch map shows you in gray is a mosaic of the pictures taken by Deep Impact during its encounter. And you can see some of the surface features. And superimposed in yellow is this little blob, which is the coverage that we are planning, the images that we are planning for our encounter on February 14th, 2011. Okay? And please notice 2 things. There's an overlap in yellow. Those are the places that have already been seen, had been seen by Deep Impact in 2005, which we will see again in 2011. That's where we'll be looking for the changes that have occurred. That's part of the experiment. The other part of the outline that has the gray part going upwards is the part of the comet that Deep Impact didn't see, that we will see for the first time, where we can, for example, see how much farther the layered terrains extend and things of the sort. Now, if you've been looking at this carefully, you'll also notice there is a bullseye. There is a red thing there. And what is that? Well, that is nothing else but the place where the Deep Impactor hit the surface of the comet. And one of the original hopes on a Deep Impact mission was to see how large a crater would be made, because the energy of the impact is well known. You know the speed of the impactor, you know the mass of the impactor, and so you would like to know how big the crater is. And as you can see, during the Deep Impact mission, the collision threw up so much material that one never actually saw the actual crater. So is the crater 150 feet across? Is it 300 feet across, as some people speculate? Why would anybody care? Well, the reason that you would care is that the size of the crater, and perhaps the depth of the crater, contains information about the mechanical properties of the surface of the comet. Well, why would you care about that? Well, the reason you would care about that is that, as Bob Farquhar said, we're always planning ahead. And we are planning missions that are intended to land on a comet nucleus and excavate material from the subsurface and bring those materials back to Earth for analysis. Now, if you're going to dig into a comet and excavate material, you need to know something about mechanical properties. So it is important to complete the deep impact experiment by actually trying to image the crater and figuring out how big it is. So that is also one of our objectives. So how are we going to do this? Well, briefly, we are on a trajectory that will take us to the vicinity of Comet Tempel 1 late in the evening on February 14, Valentine's Day. We have selected a trajectory that will get us within 200 kilometers, 120 miles of the surface. At that point, our camera can resolve things that are about 30 or 40 feet across. It's roughly the size of the stage that I'm standing on here. And that is sufficient to address these questions that we have. In this little graphic, what you see is the trajectory of spacecraft as it approaches its closest approach. The gray areas are the areas mapped by deep impact. The blue areas are new terrain that we will see that has not been seen before. And as you can see, as we come in to closest approach, the picture on the upper right, you're looking at a lot of area that has been seen before by deep impact. That's the experiment to look for changes. And then as we get closer and closer to closest approach, we see more and more blue area, which is the new territory. Okay? So we have a balance between looking for changes in what we see before and mapping new territory. Although I emphasized imaging, during the flyby, we also have instruments that will be collecting dust and analyzing dust. But the principal focus is on the imaging. And I just want to make the point that our camera is working very, very well. This is a picture taken by the camera 6 years ago or so at the time of Build 2 flyby. We have tested the camera. Everything is working just fantastically well, and we do expect to be able to take very high-resolution images during this particular encounter. So let me just finish up by telling you where we are right now. We are 158 days from encounter at this point. The spacecraft is about something like 91 million miles from the sun, about twice as far from the Earth. It's about 113 million miles from the comet. The comet itself is coming in closer to the sun. It's just outside the orbit of Mars right now. And over the next 158 days, we're going to get closer and closer and closer. And we're looking forward to a very successful encounter. We have a lot of people who are working very, very hard. The spacecraft is in excellent shape. We have a group of very hard-working people at Lockheed Martin in Denver who operate the spacecraft and are right now verifying all the commands that will be used during the encounter to make sure we get all the data that we are looking forward. We have a hard-working group of navigators at the Jet Propulsion Laboratory who are keeping the spacecraft on its trajectory to get us to this flyby that we want to effect on February 14. And of course, we have a large group of scientists, an international group that not only involves people in the United States, but people in Finland, Germany, France, a group that's anxiously waiting for the data. Okay? We haven't quite started observing, unlike Mike Hearn. Our first observations are scheduled for mid-December. We will be taking images for about 60 days on approach to the comet, but most of our high-resolution imaging will occur within a few minutes of the encounter, which, as I said again, 120 kilometers from 120 miles from the surface, late on February 14. And so that is briefly an update on Stardust Next, a great mission that we're all looking forward to. Thank you. And if there are questions, I will be delighted to answer any question.
I guess I'm going to key off a question that was asked behind me earlier, because you've got a lot of classrooms around the world, or at least the U.S. looking in. I think the real question is the difference between the non-active comets and asteroids. I mean, we're learning a lot from fragments from the creation of the solar system.
Sure.
And for students out there, what's the real difference between those two? And is there like a team comet and a team asteroid group that's both trying to find out the best they can from what they can learn from each of those on the creation of the solar system?
The question is basically what is the Right, okay. The question is, what is the difference between a comet and an asteroid, basically? And so to first order, one is mostly made of ice and the other one is mostly made of rock. And why is that, and why should we care? Well, I think Anita was talking about the early stages of the solar system when the sun was forming. Around the sun, there was a cloud of gas. And as the cloud cooled, various things could turn from gas to solid, basically freeze out. If you were close to the sun, where it was hot, ices couldn't freeze out. Only rocks could freeze out. If you were farther away, where it's colder, then you could also get ices. And so there are things that form close to the sun, like in the asteroid belt, which are mostly rocks. Okay? And there are things that form farther out in the Kuiper Belt or the Earth cloud, which have a lot of ice. Okay? And so basically, both of these things, the asteroids and the comets, are debris left over from the formation of the solar system, things that didn't accumulate into planets. And the reason they're different is because they formed in different places, different environments. Is that okay?
That brings up the question that came from that discussion. If a comet uses up all its vapor, all not the mass, but all the gases, all the conversion and moving away of the gases over the time. It disappears, all the volatiles eventually disappear. What's left, would that be called an asteroid? What is a yes. Comet without volatiles? We
understand. The question is, how does a comet die? And so, in fact, there appear to be several ways in which a comet dies. Of course, if a comet stays out in the Earth cloud where it's distant and very cold, nothing very much happens. So when it comes close to the sun, it heats up and volatiles, water ice, CO ice, just evaporate. Okay, so what happens? Well, we know of at least several things that happen. In some cases, what happens is that it's the surface layers of the comet that lose the volatiles. And it gets harder and harder for ices down deep to get hot enough and for gases to escape. So it appears in some cases that the surface eventually seals itself off where you have an inert surface of rocky and organic stuff, which is volatile poor. And so we know of examples of things that used to look like comets and now no longer show any activity. They look like asteroids. Okay, that's one thing. We also know that some comets just completely fall apart. Okay, they disappear. So those are at least two ways in which sort of comets die. But your basic point is correct, that if you're a comet, being close to the sun is dangerous because something bad will happen to you over long time scales. Yes.
Yeah, just a question that may be outside of the bailiwick of this discussion, but could you explain what are gravity waves, how they are measured, and how they may be useful in future spacecraft observation?
The question is to explain gravity waves and how they are useful. I think where the question comes from is that there is a experiment afoot called LIGO, which tries to detect gravitational waves. I mean, basically where we start is when any massive object does something like collides with another massive object, then gravity environment changes, and there is a wave that propagates. Okay, and it is hoped by some people that these kinds of perturbations that may be caused for black holes coalescing, objects that are very, very massive, that the signal can be detected at the Earth. Okay, now the question of why is this useful? I am not a physicist, so I can't honestly answer that question, okay? If there's anybody in the audience who wants to answer a question, please go ahead. Okay, I think we're good.
I have a question. So this next mission, part of it is going to be to actually look at the crater that Deep Impact created. So how likely is it that there will be a follow-up mission? You mentioned maybe to go and excavate and get some sampling from that crater, and how excited can we get about that?
Okay, the question is that there is a crater on Temple 1, and is it useful in the future perhaps to go into that region and excavate some of that material? I think the answer is yes. It turns out that Temple 1 is one of the easier comets to actually get a spacecraft to. And so if one were planning a mission to land on a nucleus, dig out some ice, bring it back to Earth, that is certainly a very reasonable target. And if you were to do that, then a very reasonable thing to do would be to get a sample from a region which was not modified by the impact and a region which was modified. It'd be a very, very good experiment to do. Unfortunately, I'm too old to write such a proposal, but I suggest that you do that. That'd be a great thing to do.
Okay. So tying into that, as you're discovering more about what the material is there plans to compare, from the meteorite samples from what may have been dead comets or asteroids to see if they're very similar in composition, how different in composition, and maybe way off in the way future, is there, the space mining ideas of asteroids or whatnot? I mean, what's the exciting place to go with all the science? And would you prefer to go to comets? I know this is Team Comet time. Or asteroids, are they equally exciting to everyone?
Right. So the question really has to do with sampling asteroids, sampling comets. The one big difference is that we do have a lot of samples of asteroids called meteorites. And if you go to Smithsonian just down the road, I mean, there are dozens and dozens of varieties, and we have begun to be able to recognize where some of these samples come from, the objects that are associated with the asteroid belt. We have to date, no one has identified a meteorite that believably comes from a comet. So the sort of quick answer to your question is, on one side, the asteroids, we've got lots of samples. We don't have everything, but we've got lots of samples. In the other case, we got nothing, okay, essentially, except maybe some of the dust that we talked about that Stardust returned, but that doesn't contain the ices, okay? So for that reason, people who study asteroids and comets, I think, are generally agreed that the next place to really return a sample from is a comet, because that's really something that we don't understand, okay?
I really didn't grasp until today just how many comets there are and have been. And there's a lot of discussion, of course, about the threat to Earth from asteroids. You don't hear much about the threat to Earth from comets. Do comets threaten Earth?
Well, the question is, we hear a lot about asteroids running into the Earth and about comets running into the Earth. And yes, there are, as Anita pointed out, a large number of comets. Fortunately, most of the time behave themselves and stay in places like the Earth cloud. But let me just point out that there are books and have been articles on what might happen occasionally when the sun and its Earth cloud is moving through the galaxy, it will pass near another star. That star perturbs or changes the orbits in the Earth cloud. Now, people have written papers of what might happen if that kind of encounter happens at a fairly close distance, in which case thousands or more of comets will suddenly be perturbed into the inner solar system. And there are people who claim that occasionally there are things like comet showers, at which time sort of the impact rate on the Earth goes up by a factor of 10 or 100 from what it normally is. Okay? So apparently comets do this sort of thing, and one of the questions that's often debated is whether the object that was responsible for the extinction of the dinosaurs was an asteroid or a comet. And it certainly could have been a comet. So yes, comets do hit the Earth, and they should get as much attention as asteroids do. But comets are also wonderful objects. Jim Green kept talking about plagues and disasters, but think of comets as wonderful windows into the past of the solar system. They're things you really want to understand and love. I think we're done.
Well, Joe, I have to disagree with you. You're not too old to write a proposal, and I've got just the one I'm going to tell you about in a little bit, and you're going to do this one.
All right, Bob's gotten me into trouble before. He's going to get me into trouble again.
Thanks again. Wow. Well, I have good news. Class is going to let out early. We had scheduled to be here until noon, so we're going to have early recess, and that's for the classrooms out there. I'm just talking about recess here, okay? Again, ladies and gentlemen, we're going to, first of all, as we wrap up, let's do a 2-for-1 here. Please give a great round of applause for our inspiring speakers and also for the Newseum and for hosting us in this incredible facility. If you want to get even more details about our speakers and about comets and the year of the solar system, again, go to www.solarsystem.nasa.gov. But there's even a bigger picture with the incredible science that's happening at NASA and the universities and other organizations working with NASA, not just here in the US, but around the world. www.nasa.gov. Ladies and gentlemen, there are some absolutely incredible missions that are going to be coming out of the NASA Science Department in all areas, particularly in Dr. Green's planetary division, but all of science all over at NASA. And they will be stunning and inspiring to the next generation of explorers. Again, go to www.nasa.gov. I want to thank you all for joining us. And for our students out there, always remember, science is not only cool, science never sleeps. Have a good weekend.